So we're about to do a lovely test. This is from Differential Equations, the first part of the course. So we're talking first order, second order, and that's pretty much it. We get to do a little bit of word problems, get to solve, do a little bit of fun calculus stuff. So we're going to have fun. As always, make sure you put your name down. Pro tip, make it legible. That way, people can read it and give us the credit that we deserve. All right, well, 6 problems. Let's go. Number 1. Use an appropriate substitution to solve the following initial value problem. All right, so we have x squared dy dx equals 4x squared plus xy plus 4y squared. And it's an initial value problem, which means we have an initial condition. Y of 1 equals 1, which tells us that when x equals 1, we have y equals 1. Okay. Now, how to begin? Well, we know we're going to make a substitution, right? And we're not just going to make any one. We're going to make an appropriate one. Well, what flavors do our substitutions come in? They generally fall into 2 categories. One is Bernoulli, and for Bernoulli, that kind of substitution looks something along the lines of u equals y to the a. And the other kind is homogeneous, and that substitution looks like u equals y over x. Now, how do you know which is which? And by the way, I should say, there's infinitely many substitutions that are possible, but these are the 2 common ones. What do we look for? Well, homogeneous actually kind of gives away what you're looking for. So you either are looking for one or 2 things. Namely, does everything look like a y over x? If it does, homogeneous. The other thing is the homogeneous really means same degree. You say, oh, look at what you have. So here we have x squared, degree 2. X squared, degree 2. Y squared, degree 2. And xy, well, how do you compute the degree? You add the 1s, it's degree 2. Same degree. So that's our substitution to make. Now you might say, wait, hold on. What about Bernoulli? What is that? Well, Bernoulli has a very, very particular form. So Bernoulli says, look, I have y prime plus stuff y equals stuff y to the a. All right? And I haven't filled in the boxes, but the boxes just say, some function of x. And unfortunately, we're not in that form, right? Sure, we have a y prime, but the problem is, I have a y, and I have something with a y to the a, but there's this extra piece here. And so I'm really sure I have 3 pieces. This one has 4. 1, 2, 3, 4. So not going to work out. That's okay. We're in the homogeneous scam. And speaking of which, given that y over x is our substitution to make, what we can do is we can start with our original equation and do what? Well, we're going to make it look like everything has a y over x. So I'm going to multiply both sides by 1 over x squared. And so we get dy over dx is equal to 4x squared times 1 over x squared, 4. X times y times 1 over x squared, y over x. And now 4y squared times 1 over x squared is going to be a 4y over x squared. Okay, now, that we haven't done any substitution yet. That was our rewrite. Now, the substitution. Well, it's easy to say what happens to the y over x terms. Those become u's. So there's a u, there's a u squared. Don't need to do anything with the 4. But now the dy dx. And here's the fun thing. If our substitution is u equals y over x, solve for y. Y equals u times x. And when we write down u, just keep in mind that we write this down. We're going to say, u is a function of x. We don't explicitly say that, but we know that. So now we're going to take the derivative of everything. And when we do, well, what do we have? We have derivative of y with respect to x, product rule. So we'll take the derivative of the first, which was our u prime, times the second, x, plus the first times the derivative of the second, which is 1. So that says dy dx becomes u prime x plus u. All right, so we put all this together, and we get the following. There we go. So there's the substitution. All right, success. And if we've lived a good life and we've updated things correctly, good things should happen. We see we can cancel the u's. That's good. And by the way, I should have said u prime. That's our du dx. So this becomes du dx times x. And here I can pull out the 4 for 1 plus u squared. And homogeneous, if we encounter homogeneous 100% of the time, I like those odds, by the way. I love the odds of 100% of the time. It's going to be separable. So we're going to put the u's on one side. So this becomes du over 1 plus u squared is equal to 4 over x dx. And now we're doing great. We've separated, right? Separate, integrate, uncomplicate. Well, so we'll integrate both sides. Integral 1 over 1 plus u squared. Is it my birthday? Ho, ho, ho. It feels like it, because that's an arctangent. Woohoo! Arctangent u. Arctangent u. Yeah. Arctangent u. Wow, wow. All right. Sorry, just got a little excited there. Arctangent u. Integral of 4 over x. Well, that's 4 log x. And don't forget, you need a constant somewhere. Now, let's, whoops, I need something from up here. We have some initial conditions. Don't forget about your initial conditions. So let's plug those in. All right. So, updating, we need to do two things. One, what is u? It is y over x. So we now have arctangent of y over x is equal to 4 log x plus c. Notice this is most of our solutions. There might be some other solutions floating around, but this is essentially it. Let's plug in our conditions. So remember we said x equals 1, y equals 1. So we get arctangent of 1 equals 4 log of 1 plus c. But arctangent of 1, that's pi over 4. Log of 1 is 0, so we come to the conclusion c is pi over 4. So we're basically done. We have the following, that arctangent of y over x is equal to 4 log of x plus pi fourths. Now, one of the things that can be hard is knowing when to stop. Sometimes I'll say this is enough, and sometimes I'll say solve for y. I'm of the opinion, this kind of one, I feel like I should solve for y, because there's just a single y. If I have multiple y's, it's like, forget it. But one y, I want to do it. How do I get rid of arctangent? I'll take tangent to both sides. Arctangent is the inverse of tangent. So doing that, we get that y over x equals tangent of 4 log of x plus pi fourths. And now multiply it across by x. And we come to the conclusion y equals x tangent of 4 natural log of x plus pi fourths. Exactly, right? It was like, That was it from the beginning, right? Right? Probably didn't see it right away, but we got there. We got there. All right. Number 2. Find an implicit solution to the following initial value problem. And they give us a bunch of stuff. Passing through the point xy equals 0, 2. Include justification that this is an exact equation in your answer. So, spoiler alert, they gave it away. Exact. Now, they kind of gave it away earlier when they said implicit solution. There's not a lot of things where we get to a point where we must have an implicit solution, but one of them is exact. The other thing is the way this is written. So you have something dx plus something dy. So there's lots and lots of clues that this is exact. Of course, the biggest one is the best one when they tell it to us. And, we're not going to, ignore their advice. They give out pretty good advice. And so we say, okay, so we know it's exact. So what does that mean? Well, what that's telling us is the following. It says that this has a very particular form. So we have e to the y plus cosine of x dx plus 3y squared plus x e to the y dy equals 0. And now this part right here, this e to the y plus cosine of x, since it's attached to the dx, it's like you took the derivative of something with respect to x. And this part right here, since it's attached to the dy, it's like you took the derivative of something with respect to y. And our goal is, what's that something? So, idea. We have the derivatives. And so we can use that. So here's the process. We're going to go through 2 stages. Stage 1 is we're going to say, let's use this piece. So I'm including the dx here very deliberately. So what do we have? Well, we have the following. We're going to say integrate e to the y plus cosine of x dx. And what that means is when we're integrating, we're thinking the thing that can vary is the x term. What do we do with the y's? Well, the y's aren't the thing we're integrating. So we treat those as constants. So this e to the y, we treat like a constant. So that would be x e to the y. So like constant x. Integral of cosine is positive sine. And now, plus a constant, but a constant with respect to x, which means there's something which could depend on y. All right. Well, that's all well and good. Right? Phase 1 in some sense. Now, phase 2. Do the same thing, but with the other piece. Okay. So, we're going to follow this around. So we're going to integrate our 3y squared plus x e to the y dy. So now we're integrating with respect to y. Y is the variable. Treat x as like constant. Integral 3y squared with respect to y, that's y cubed. Integral of x e to the y dy, so x is like a constant. Integral of e to the y is e to the y, so it's x e to the y, plus anything which is constant with respect to y, so that can be anything that just depends on x. All right, now, moment of truth. Here is where we find out if we have an exact equation. We say, okay, look at the pieces which have both x and y. So there's x e to the y and x e to the y. These parts match. And that's the test. So since the parts with both x and y match, it is exact. All right? So that's the justification they were looking for. Okay, so we have those parts, but we have some other parts, right? We have the y cubed part, and we have the sine x part. So, what is f? And here you go. You do the following. So our function that we were after, f, is the overlap, okay? That pieces that were in both, and they had to agree. Anything with just x, that gets thrown in. Anything with just y, that gets thrown in. Now that's f up to a constant, and so you set this equal to some constant here. Okay, so here, this is sort of the generic solution. All right, good. Okay, now, with all of that out of the way, well, are we done? No, right? Because they gave us a point. They said, we're going to go through that point 0, 2. So, we haven't yet used this information. So what do we know? When we plug in x equals 0, y equals 2, we say, well, what do we get? Well, we get the following. We get 0, right? X equals 0 times e squared plus sine of 0 plus 2 cubed. Right? That's just plug in x equals 0, y equals 2, and all that equals e. Well, we go 0, 0, and that is 2 cubed is 8. Okay, so our final answer is x e to the y plus sine of x plus y cubed equals 8. Ta-da! Now, before we leave this, we talked about how to justify that it's exact. And I like this method, which says, while in the process of finding the solution, I'll pause and say, aha, these parts match, therefore it's exact. There is a second method to do it, and both methods work. And so here's the idea. So I'm going to come back up here. Whatever is in front of your dx, let's call that m. And whatever is in front of your dy, well, let's call that n. So here, it's like you started by taking derivative with respect to x. Here, you start by taking derivative with respect to y. Now, do the opposite. So take what we call the derivative of m with respect to y, and here, take the derivative of n with respect to x. The question is, are they equal? If the answer is yes, exact. So equal if and only if it's exact. So what happens here? So if I take the derivative of this term with respect to y, what happens? You get e to the y. If I take the derivative of this term with respect to x, what happens? You get e to the y, right? Because that goes away, derivative of x is 1, and you say, aha, e to the y is e to the y, therefore it's exact. So this is oftentimes the solution you'll see in the book, and depending upon where you go. And this is true. It works. It works. And there are some times when this is a preferred method. But if you're actually solving, I feel this is a faster way to do it. But the point is, you get the credit for doing the right thing. Do what you're comfortable with. Do what is best for you. It's your test. Invest in it. All right. Number 3. Consider the following autonomous differential equation. Autonomous. Well, what does that mean? There's no t's. It's only y's. And so we say, okay, so our dy dt, 3 times y plus 1, y minus 2 squared, y minus 6 squared. And it says find the critical points, draw the phase diagram, and then classify each critical point. All right, now, when you see an autonomous differential equation, what's going to happen? Well, the good news is we almost never solve these because they can be very, very painful to solve. But the key here is you should channel your inner Calc 1 student and you should say, oh, okay. And basically, you're going to say, first derivative test from Calc 1. That's going to be our philosophy as we think about things. What is the first derivative telling us? All right, so for critical points, channel your Calc 1. What would your Calc 1 inner child say? It would say, you're awesome. I'm so proud of how good you've gone at derivatives. Then it would say, hey, critical points, that means derivative equals 0. So you're like, exactamund. So that says we need to take dy dt to 0, or we have that 0 equals 3 times y plus 1 times y minus 2 squared times y minus 6 squared. Well, that's factored out, and we say, okay, well, this says y equals negative 1, y equals 2, and y equals 6. Those are the times when one of our pieces is 0. So these right here, these are our critical points. All right, so that was quick. Ta-da! Whoop! Now, phase diagram. Okay, so what's that going to be? Well, that's going to be a line. We're going to order these. So the good news is they're already ordered for us. Minus 1, 2, 6. So we go minus 1, 2, 6. They don't have to be exactly spaced. I understand minus 1 to 2 is smaller than 2 is to 6, but that's not the point here. Now, what do we need? Well, what we need to do is figure out what's happening to y prime. And so we plug in values. So let's suppose we plugged in a large negative value, like negative 2. If you plug in negative 2, the 3 is positive, that'll be negative. And because you're squaring here, it's positive, and you're squaring here, it's positive. So positive, negative, and positive, positive. So what does that tell us? It means that dy dt, or y prime, is negative. Okay, so y prime less than 0. Let's keep going. Plug in 0. Positive, positive. Remember, squaring positive, squaring positive. So that says, hey, dy dt is positive, greater than 0. All right, plug in 3. Positive, positive. This will always be positive. This will always be positive. Great. Y prime's positive. So, all right, plug in something bigger than 6. 100, or 7, or 20. Anything convenient. Positive, positive, always positive, always positive. So y prime greater than 0. Now, here's the translation. When y prime is negative, that says y is decreasing. Well, what does it mean to be decreasing? It means we're going down. Down, 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 we're going down. Woohoo! Okay, so in terms of the number line, which way is down? It's to the left. So we are heading off in that direction. Now, when y prime is positive, what does that mean? It says we're going up, 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 right? So, right, because we're increasing. Which way is increasing? To the right. Okay, so we're moving upwards. So up, up, and up. Now, that's the phase diagram. Okay, so here's our phase diagram. Cool. Final part to part A. Classify. So when it says classify, there's 3 options. So let's just remind ourselves. So we have the stable, that says we're going in from both sides. We have the unstable, that says we're heading out from both sides. And then we have sort of half and half. And so we're sort of passing through. Now we could be going to the right on both sides, not unstable, semi-stable. Could be going to the right on both sides or to the left on both sides. Okay, good. So we just follow the arrows. We say, well, what's happening at 1? We're going out on both sides. So what does that tell us? Well, that tells us that, I think I said 1, negative 1. Negative 1 is unstable. Okay, now how about 2? We're passing up and up. That's semi-stable. So 2 is semi-stable. Right? Once you have the phase diagram, you just read off the answer. Up, up. So 6 is semi-stable. All right, good, good. That's that. Okay, now that's part A. We've finished the classifying. On to part B. Given that y of 0 is equal to 4, using all available information from the phase diagram, sketch a typical solution curve on the xy plane below. So in particular, not atypical, but like, what does that y look like? What's best guess? Now, this phase diagram, that's the one that we're referring to, I'm going to replicate it. So I'm going to take it and turn it sideways here. Okay, so let's see. Oh, there we go. All right, beautiful. So we have our phase diagram off to the side. Just for reference, here's our phase diagram. And so we have negative 1, we have 2, we have 6, and now notice from negative 1 we're going down, and then from negative 1 to 2 we're going up, 2 to 6 we're going up, and then 6 above we're going up. Now what are we told? We're told that y of 0 equals 4. So that's a point. So we come in and say, well, when you plug in t equals 0, you get 4. So we have that 1 point. Now, where does that fit in this phase diagram? So 4 is in between 2 and 6. So I'm going to draw horizontal lines at 2 and 6. Now this is not part of the curve, but these are some reference points. So in particular, y equals 2 and y equals 6 are both solutions. So I can't go past 6, can't go below 2. So I'm going to try to approach them. Now the question is, are we going up? So in other words, we come off 2, then pass towards 6, or are we going down, off 6 towards 2? And that's when we come and say, what does the phase diagram tell us? It says we're going up, up, up. It's our moment. Gonna be going up. Gonna be going up. Oh, ho, ho. Oh, wait, sorry. All right, so we're going up, right? So we need to come off from 2, pass through 4, and then sort of approach 6. So we don't hit 2, we don't hit 6, but we come off close from 2, pass through, and then head towards 6. And that's the picture. All right? So the key, mark your point and know where you're going between. And know, are you going up or down? So that's where the phase diagram comes into play. Where are your asymptotes? And how are you going between? Okay, so that's not too bad. I love these kinds of problems. They're some of my favorite. Okay, number 4. We're halfway done. So we have the particular solution. So that means somewhere out there's a differential equation, and this is a solution to it. And we have minus 4 cosine 2x, plus 5 sine 2x, and plus 6 e to the minus 3x. And it says, compute the Wronskian of the solution functions and describe why you know that they are linearly independent using that result. Okay, so first off, what are the solution functions? Well, you look for the pieces. So don't worry about the coefficients, just focus on the functions. So cosine of 2x, sine of 2x, and e to the minus 3x. So those are our 3 pieces. So we have 3 functions. So how do you form your Wronskian? Well, since we have 3 functions, what we're going to have is a 3 by 3 matrix. And so in the first row, you're going to put your functions. And then in the second row, you're going to put your derivatives. And then in the third row, you're going to put your second derivatives, right? So in other words, you start with the functions and then you just keep taking derivatives. So it doesn't matter which order you put them in. Now, I'd recommend putting them in the order that they're written down, not because there's anything special about that order, but because that's probably what they're looking for and anticipating. And that means that's how they're checking. And let's make it easy for them to see that we're doing good work. Now, take derivatives. Okay, derivative of cosine is negative sine. Don't forget the chain rule. So minus 2 sine 2x. Derivative of sine is positive cosine. Again, don't forget the chain rule, 2 cosine 2x. And I should have given myself more space. Derivative of e to the minus 3x is minus 3 e to the minus 3x. Derivative of sine is cosine. So we already have a minus 2. There will be another 2. So that gives us minus 4 cosine of 2x. Derivative of cosine is minus sine. We'll also have a 2 coming out, so that's minus 4 sine of 2x. And again, we'll have a minus 3 coming down, so that's 9 e to the minus 3x. Now, I said set up a 3 by 3 matrix, but for the Wronskian, really it's a determinant. And ultimately what the Wronskian is doing is it's saying, hey, you've got 3 functions. How different are they? Right? And so that's the goal. Is it like, well, is there a redundancy? That's what you're asking. And the way you check for redundancy is say, well, you can't combine 2 of them and get the third. So what do? Well, we need to do this determinant. And how do you do it? Well, however you like doing determinants. There's 2 general schools of thought. There's cofactor expansion, which is really easy to do if you're used to it, and easy to also make mistakes if you forget about things like there's a plus minus kind of thing going on. The other thing is diagonals. And that's the way I'm comfortable doing it, so I'm going to do it that way, but do it the way you're comfortable doing it. It's your test. You're the one who has to take it, so make sure you can feel comfortable doing it. So diagonals, how does it work? Well, we're going to go on all the diagonals, and there's 6 of them. So there's 3 going down, and there's 3 going up. Now you might say, well, wait a second, you're out of space. Well, you wrap around, right? Okay, so cosine 2x, 2 cosine 2x, 9 e to the minus 3x. So I'm going to mark these with some colors here. So I have my first diagonal is that one. All right, so that would give us 2 times 9, that's 18 e to the minus 3x cosine squared of 2x. Okay, so we're computing our Wronskian, which is this determinant. That's diagonal 1. Okay, diagonal 2. We have sine of 2x minus 3 to the minus 3x and minus 4 cosine 2x. So minus 3 times minus 4 makes a 12. So there's a plus 12. We have a sine and a cosine. So sine of 2x, cosine of 2x, and don't forget the e to the minus 3x. And one more diagonal going down. So we have e to the minus 3x, minus 2 sine 2x, minus 4 sine 2x. All right, minus 2 times minus 4 makes a plus 8. So we get plus 8 e to the minus 3x sine squared 2x. Okay, so round 1 is done. Still 3 more diagonals to go. Now the other one's going to go uphill. Now, the thing about the uphill, you got to remember this, is you add the downs, subtract the ups. So we have minus 4 times 2. That makes minus 8. So we're going to subtract minus 8 cosine, cosine. That makes cosine squared, 2x. And then the e to the minus 3x. Okay. Now, the next one. We have this one. Again, wrapping around. So we've got minus 4 times minus 3, that's 12. Positive 12, but we're going uphill, so we have to subtract it. Subtract 12. We have a sine and a cosine, and an e to the minus 3x. So sine 2x, cosine 2x, e to the minus 3x. And our last diagonal, 9 e to the minus 3x, minus 2 sine 2x, sine 2x. Okay, so 9 times minus 2 makes minus 18, but we subtract that. And there's an e to the minus 3x, and there's 2 sine squareds. All right, there we go. Now, clean it up. And if you've lived a good, clean algebra life, nice things should happen. Do nice things happen here? Yes, those middle terms cancel. They're the same except for sign. One's plus, one's minus. Woohoo! What else do we see? Well, here, 18 plus 8. So that gives us 26. Cosine squared, 2x, e to the minus 3x. Over here, minus minus makes a plus. So 8 plus 18, again, 26. Sine squared of 2x, e to the minus 3x. Well, they both have 26. They both also have e to the minus 3x. So 26 e to the minus 3x times cosine squared of 2x plus sine squared of 2x. Oh my gosh, it's happening! It's happening! Well, wait, what's happening? This is 1. So, our Wronskian, 26 e to the minus 3x. That's the Wronskian. Whew! Done. Done. Now, we're not quite done with part A. We have successfully computed the Wronskian. We've done the hard part, but there's one other piece. It says, describe why you know they are linearly independent using that result. Well, what follows? And here's the clue. So, 26 e to the minus 3x is never 0. And you might say, okay, what's that have to do with it? Well, linear independence comes from saying that the Wronskian is never 0. That's what says there's no way to combine these to get something weird happening. In particular, this implies linear independence. So that's what you're looking for. You're looking for saying, hey, is your Wronskian 0 or non-zero? Sometimes it's always 0. That means there's a redundancy. Sometimes it's 0 at just a couple of points, and it says, well, solutions sort of somehow weave together at those points, then weave back off. But the ideal thing is to say it's never 0. Now notice 26 is never 0, but also one of the nice things about the exponential function, it's a beautifully optimistic function. It always looks at the bright side of life. And it's always positive. All right, so that's part A. All right, now part B. Give the unique third order homogeneous differential equation with constant coefficients that y is a solution for. Okay, now, can we use our Wronskian? Well, not really. That's not what the goal here is. So what can we do? Well, we can say, let's think about what's going on. Now, these come from solutions of constant coefficient differential equations, or at least they can. What are the roots? Well, when you see the cosine or sines, that means they come in pairs. So those come from complex roots. And in particular, that's going to come from plus or minus 2i. The 2 being the part that there's a cosine, or the sine, the inside piece. There's no real part, because the real part would be attached as an exponential function. The e to the minus 3x, well, that says there's a root of minus 3. So we know the roots, plus minus 2y and minus 3. Now you might be saying, wait, roots to what? Well, what we do is we create the auxiliary polynomial. And the hard part about this is spelling auxiliary. And I don't know if I did it right, but that's okay. I'll get partial credit. So we have our roots. And so I'm going to write this down. Roots plus minus 2y and negative 3. Okay, so those are the roots we mentioned already. So our auxiliary polynomial, well, for a root of negative 3, that would be r minus minus 3. And for complex, and in particular, plus minus 2i, that would come from r squared plus 4. All right, so we set that equal to 0. Well, minus minus is really a plus. Now I'm going to expand this auxiliary polynomial. Since we had the roots, we had the factored form. Now expanded. So we'd have an r cubed. Okay. We'd have a 3r squared from 3 times r squared, a 4 times r, and a plus 12. All right, now here's the fun thing. From the roots, we got the factored auxiliary polynomial, which means we have the unfactored auxiliary polynomial. And now the auxiliary polynomial, we turn into a differential equation by saying, aha, ho, ho, ho. You say the power becomes the order of the derivative. So r cubed, third derivative of y. R squared, second derivative of y. R, first derivative. And then you say, well, what about this 12? That 12 becomes the 0th derivative. So write it as y equals 0. And what do we have? Well, it's a third order, homogeneous, that means equals 0. It's a differential equation, constant coefficients. And because we got the roots that we wanted, in other words, the roots that this would come and make, that's going to be the one that we're after. All right, so it's kind of like running the process backwards, right? We know how to start with constant coefficient and say what's the form that says, hey, here's an example of the form. Now run it backwards. And but there you go. There you go. All right, well, still a few more problems, right? Focus. Focus. We can do this. Find the general solution to the following differential equation. 2y double prime minus 4y prime minus 6y is 7 e to the negative x. Okay, now over here, what do we see? We see stuff. What does that mean? It means more work. In particular, this tells us, this is a non-homogeneous. So the question is, hey, does it equal 0 or not equal 0? So when you have non-homogeneous, you're going to split it into phases. So initial process. Say, well, let's pretend like it was homogeneous. So we're going to set 2y double prime minus 4y prime minus 6y equals 0. So we're after the homogeneous part. So set the right-hand side to 0. Well, now we're sort of back in the previous problem where we're going to turn it into an auxiliary polynomial. 2r squared minus 4r minus 6 equals 0. You can factor a 2 out. R squared minus 2r minus 3. And you should anticipate that these will factor because they like you. They want good things to happen. When I say they, your teachers. Your teachers are the friendliest people in the world. And so this does factor r minus 3 and r plus 1. Check it out. Check, check, check. Check it out, right? R squared, good. R minus 3r minus 2r. Minus 3, 1, minus 3. So we get roots of 3 and negative 1. Now, what does that tell us? Well, it tells us that our homogeneous solution, all right, y sub h for homogeneous. I think sometimes it's YC for complementary. Okay, yeah, that's probably the notation. YC, complementary solution. Ah, you look wonderful. Okay, so that looks like, well, some constant, e to the 3x, and some constant e to the minus x. All right, so that's the homogeneous part. Okay, so homogeneous part. Now, we change gears. So, okay, got that out of the way. Now we got to focus on the non-homogeneous part. So we're going to have to be after a particular solution. And here's where we're careful. We say, let's look at our solution. It looks like, the right-hand side, that non-homogeneous part. And let's compare it to the generic homogeneous solution. And there's a couple of things that can happen. Well, there's kind of two things that can happen. No overlap and overlap. Which one are we in? Well, overlap. So, what do we do? Okay, here's our approach. So, once we found our homogeneous, we're going to look for a particular solution. And our default way to do this, if the non-homogeneous part looks nice, is we're going to do it by method of undetermined coefficients. All right, so that's our thinking. Method of undetermined coefficients. Or essentially it's like method of really good, wise, informed guess. I like that. You know, it's not like a random guess. We know what it looks like. We just got to kind of figure it out. So, if we didn't see the homogeneous part, we'd say, well, you see that e to the minus x? That should say our particular solution should have something, some constant c, and an e to the minus x. Now that's if that's all we see. But we come and say, check to see if there's overlap, and say, uh-oh, overlap. What do you do if there's overlap? Well, you've got to bump it up. What do I mean? Well, add in a high enough power. Now, the good news is there was only one term, so we only have to bump up the one term. So our particular solution looks like this for some c. Not for arbitrary c, but for some particular c. So the question is, which c? Okay, so to figure that out, we've got to plug it in. So we're going to take our first derivative, and we're going to do a product rule. Derivative of the first, well, that's just 1. So c e to the minus x plus c, and then x times e to the minus x, so that's derivative of e to the minus x is e to the minus x, and we'll change this plus to a minus. All right, c e to the minus x minus cx e to the minus x, yp double prime. All right, well, a minus comes down, so minus c e to the minus x. Product rule again, so that's minus c e to the minus x, right? Because derivative of the first is 1 times the second. Then minus cx. Now the derivative of e to the minus x is e to the minus x, but the minus comes down. Minus makes plus. We can put these two terms together at the start. Minus 2c e to the minus x plus cx e to the minus x. And now we have our pieces. Okay, so here we go. We have the following. 7 e to the minus x is equal to 2 y double prime. So that would be 2 times minus 2c e to the minus x plus cx e to the minus x. Okay, that's 2y double prime. Minus 4 times y prime. That would be c e to the minus x minus cx e to the minus x. And then minus 6, okay, that was the middle term. Then the last term, minus 6, y. Well, that's cx e to the minus x. Okay, well, let's do some computing. Now, let's work on these terms. You'll notice there's no x e to the minus x term. You might be saying, uh-oh, trouble. But check it out. If you've lived a good, clean algebra life, this should disappear. 2 times cx e to the minus x plus 4, right? The minus 4 comes in, plus 4 cx e to the minus x minus 6 cx e to the minus x says that that part adds to 0. And that's what should happen. Not coincidence, but design. Now, over here, you have minus 4c, and, well, nothing. So minus 4 makes minus 8 c e to the minus x. And, well, you now compare, and you say, well, you can cancel the e to the minus x's. And what do we get? 7 equals minus 8c, or c is negative 7/8. So we're almost done. We now have that our particular solution, yp, is minus 7/8 x e to the minus x. So how do we get our total solution? We put the two together. So our generic solution looks like the following. We did our homogeneous, we did our particular, and so we get y is our homogeneous plus our particular. So we have a e to the 3x plus b e to the minus x minus 7/8 x e to the minus x. Woohoo! Nice! All right, that's number 5. Only one more to go. Number 6. Consider the following initial value problem for a spring dashpot system. And if you're looking at this and saying, oh, what? What's a dashpot? Well, a dashpot is just another way of saying there's a damper. All right, so we have a spring, which is trying to be very springy, but a dashpot is saying, whoa, slow down, and it's trying to help make sure the system somehow stabilizes. All right, so we have a differential equation, we have some initial conditions. Find an equation that expresses x in terms of t. Now that's just a fun way of saying solve. Classify as underdamped, critically damped, or overdamped. Now underdamped says what? Well, it says you still behave spring-like, but there's some damping going on. So this comes from what we'll call complex roots. And we'll see what we mean by roots in just a second. That's, well, okay, I'll just say it now. Auxiliary polynomial, complex roots. Critically damped, this is the sort of, in some sense, the ideal amount of damping for the spring. It says if you start springing, this amount of damping will help you return your system as quickly as possible to stable. So it's like just like chef's kiss of damping. How do we recognize it? That's repeated roots. So in other words, the same root multiple times. And overdamped, well, that just says you have such a powerful damper that your spring doesn't look like a spring. It does, there's no up, down. Okay, so how do we recognize this? Real roots. So we don't see any of that sine or cosine entering the system. So we'll actually know, before we finish this problem, we'll know which one of these we are. Okay, so here we go. We have a nice constant coefficient, homogeneous, our favorite kind of differential equation. So we start by saying x double prime plus 4x prime plus 29x equals 0. Turn that into an algebra problem, the auxiliary polynomial. You know, this class is basically an algebra class with the fun calculus candy coating on the outside. All right, now from here, we're going to solve for the roots. There's a couple of ways to do it. It just depends on what you're comfortable with. I'm just going to go ahead and see if I can't do it by using quadratic formula. An oldie but a goodie. Completing the roots will also work pretty well here. Sorry, not completing the roots, completing the square. But okay, so r is equal to negative b plus or minus square root of b squared. So that's 4 squared minus 4ac all over 2a. Okay, so let's see, what does that become? Negative 4. And, well, actually, notice here we have a 4 and a 4. I'm going to pull that out. So that's square root of 4 is a 2. And we'll get 4 minus 29 over 2. So, okay, so that's a negative 4 over 2 is negative 2 plus or minus. Here the 2's cancel. And 4 minus 29 is negative 25. And that means what? It means square root of 25 is 5. So negative 2 plus or minus 5i. So before we go on, let's finish the classifying. So classification comes from knowing your roots. Our roots, they are complex. So we still are spring-like. So we are underdamped. So underdamped, still spring-like. Now, just a reminder, the real part, this is what goes inside the E part. And here, the imaginary part, this is what goes inside the sine and the cosine. Right? So make sure you know where the real part goes and where the imaginary part goes. So now we can say generically, what does a solution look like? Well, now that we have the roots, so our generic solution looks like x of t is some constant a, e to the minus 2t, cosine 5t, plus some constant b, e to the minus 2t, sine of 5t. Right? The minus 2's go inside the exponential parts. The 5, because it's attached to the I, goes inside the trig parts. So the only thing left, what are A and B? That's where the initial value comes from. Okay, so we know what happens when we plug in 0. We are told 2 is equal to x of 0. Well, we get A, and then we have e to the 0 is 1, cosine of 0 is 1. So A times 1 times 1, plus b, e to the 0 is 1, and sine of 0 is 0. So that goes away. So that tells us, aha, a equals 2. We're halfway done. We needed to solve for two things, a and b. We got the a. A was a freebie. Woohoo! Yay us! Yay us! But that means we have another half, probably going to be a little bit harder. All right, but we can go ahead and update. So, doing a quick update, we have x of t is equal to, a is 2, e minus 2t, cosine of 5t, plus b e minus 2t, sine of 5t. We now come to this other piece of information. X prime of 0 equals 1. So, if we want to use x prime, we got to take a derivative. All right, it's coming. So, be patient. No need to rush. We still have plenty of time left. X prime. All right, product rule. Derivative of the first, derivative of e to the minus 2t, and minus 2 comes down. So that's minus 4, e to the minus 2t, and then the second. All right, derivative of the first times the second, plus the first, 2e to the minus 2t, times derivative of the second. Well, derivative of cosine is minus sine, and there'll be a 5 that comes out. So adding that to the 2, we'll write this as minus 10, 2 times 5, e to the minus 2t, sine of 5t. Yes, it's going to go away, but still make sure it's right. There's some graders are they check everything. They are like hawks looking for every possible thing. Okay, do the same thing with the second. Get rid of the first, minus 2 comes down, right? Get rid of e to the minus 2t, minus 2 comes down. So minus 2b. Oh wait, is it minus 2b or not 2b? That is the question. It's minus 2b. That's right. All right, so 2b, e to the minus 2t, sine of 5t, right? Second. Now, derivative of sine. Positive cosine, chain rule of 5 comes out. So plus 5b, e to the minus 2t, cosine 5t. Okay, what do? We're going to plug in 0 when you get 1 out. So, here we go. 1 equals x prime of 0 equals, well, we're going to get from the first term, right? E to 0 and cosine 0 is 1 and 1, so we get negative 4. And then minus 10 times 1 times 0. So that's a 0. And 2b times 1 times 0. So that's a 0. All right, well, lots of zeros. And here we get a 5b, 1, and a 1. So, okay, so that's a plus 5b. Now what can we do? We add 4 to both sides. So 5b equals 5, or b equals 1. Good. So, one more update. We can now put in what b is. So we have our solution. X of t is 2 e to the minus 2t cosine 5t plus e to the minus 2t sine of 5t. And as I mentioned, we already classified it as underdamped. And that was it. Our final problem. Whew! We still have plenty of time left over to celebrate and appreciate our efforts. Thanks for coming and joining. I hope this helps. Work hard and study. You can do these things. You have the ability. I believe in you. All right. Good luck, and hopefully I'll get to see you again. Bye.